Let us discuss some properties of the rotation matrix. I assume that we know what a rotation matrix does. There could be two interpretations of what a rotation matrix does. The first is that it describes one frame relative to the other. And in this interpretation of the rotation matrix, if we have one frame, which is, say, the fixed frame, let us name this frame A, and I have another frame which is rotating with respect to frame A. Let us call this frame as frame B. In this case, if I have a rotation matrix that describes frame B relative to frame A, then this rotation matrix will be a 3 cross 3 rotation matrix, and it will have 3 columns, and each column of this rotation matrix is basically, the first column is the x direction of frame B expressed in frame A. The second column is the y direction of frame B expressed in frame A. And the third column is the z direction of frame B expressed in frame A. From this very interpretation of the rotation matrix, I can understand that there are certain conditions on the columns of the rotation matrix. The first condition is every column is a unit vector. The second condition is that the columns are orthogonal, right? So a rotation matrix is an orthogonal matrix. This is the first fact. The second fact is that the determinant of the rotation matrix is equal to 1. It is equal to 1. A third fact about rotation matrix is that all rotation matrices are, of course, orthogonal matrix. And in general, these are 3 cross 3 matrices, right? But they also form a group called the orthogonal group. So what is this orthogonal group? An orthogonal group is a group of all rotation matrices that have their columns perpendicular to each other. Now, the rotation matrix in particular is called a special orthogonal group, where special denoting the fact that the determinant of the rotation matrix is +1, right? So there could be other rotation matrices that have a determinant of -1. So they are also orthogonal. They are a part of the orthogonal group. But rotation matrix have a determinant of +1, and they form the part of a special orthogonal group. Also, we can have another interesting fact about the rotation matrix. That is, if we do R transpose, I will get the identity matrix. This is also easy to see from the original definition of the rotation matrix that we have defined here, because anywhere we have the dot product between the same directions like x and x, we'll get a 1, and those will be along the diagonal elements. And wherever we have the dot product between x and y, x and z, y and z, z and x, there we will get 0, right? Because they are perpendicular. So ultimately we'll arrive at the identity matrix. So these are some of the properties of the rotation matrix. Another important or interesting thing that we can mention about rotation matrix is that since the determinant of the rotation matrix is 1, it does not scale any vector it is operating on. It only transforms it, or it only rotates it, right? So it does not scale. So thanks a lot.